Section 4.3 Transposition. The second major cryptographic tool is transposition, changing the order of the characters in a message. The simplest method is root transposition. The letters of the message are written into a grid in one order and read out in a different order. This section gives a quick look. The full discussion is in Chapter 7. For example, the message "There is no love among thieves," which has 25 letters, is written into this 5x5 grid from left to right across the rows and read out from top to bottom down the columns. The leftmost column in this grid is TIOOI when read from top to bottom. Common routes for writing the letters into the grid and for reading the letters out of the grid include going straight across the rows, either left or right, straight up or down the columns, alternating left and right across the rows, alternating up and down the columns, diagonally starting at any corner, diagonally in alternating directions, or spiral clockwise or counterclockwise, either inward or outward. Root transposition ciphers are rated 1. Section 4.4 Fractionation. Fractionation is the division of characters into smaller units. We have already seen one way, representing a character as a binary number. Each bit of that binary number can be manipulated as a separate unit, substituted, or transposed. This section introduces fractionation. There is a detailed discussion in Chapters 9 and 10. A classical way of representing a letter as 2 digits is the Polybius square, invented in the 2nd century BCE by the Greek historian Polybius. Here is a 5x5 square using a mixed alphabet with the keyword sample. Notice that the letters I and J share one cell in order to make the 26-letter alphabet fit into the 25-cell grid. Since A is on row 2 in cell 3, it is represented by 23. B is 33, C is 34, and so on, through Z represented by 21. I and J are both represented by 44. These digits can then be substituted, transposed, and regrouped in various ways. Pairs of digits can be turned back into letters using this grid, or another Polybius square arranged in a different mixed order. A modern version would replace each character with its hexadecimal representation in ASCII or UTF-8 code. Thus A equals 41, B equals 42, C equals 43, through Z equals 5A. These hexadecimal digits can similarly be substituted, transposed, regrouped, and turned back into bytes. A fun example is fractionated Morse, invented by M.E. O'Haver in 1910. O'Haver always went by M.E. because he disliked his first name, which was Merle. Historical note. A footnote on page 241 of Craig Bauer's Secret History, The Story of Cryptology, states that M.E. O'Haver was one of the pseudonyms of prolific pulp fiction writer Kendall Foster Crossan. This is not true. Crossan sometimes used the pseudonym M.E. Chaber from the Hebrew Mechaber, meaning author. In fractionated Morse, the letters are taken in groups of a fixed size, say 7, and replaced by their Morse code equivalents using / as a letter separator. Then the lengths of the code groups are reversed, and the resized groups are turned back into letters. Morse code was invented by Alfred Vail in 1840 and named for his employer, Samuel F. B. Morse. This cipher has several obvious weaknesses. Since it uses the standard Morse alphabet, the only key is the length of the letter groups, which can be guessed in just a few tries. Plaintext letters are often replaced by themselves. There are 30 different Morse code groups, but only 26 letters, so 4 extra characters are needed. O'Haver used Germanic, A umlaut, E umlaut, O umlaut, and U umlaut. Fractionated Morse is rated 1. These problems can be partially fixed with two changes. 1. Use only the Morse group of lengths 1, 3 and 4. There are 26 such groups, perfectly fitting the 26-letter alphabet. 2. Scramble the order of the alphabet, or equivalently, scramble the order of the Morse code groups. I call this enhanced version FR Actionated Morse. For example, using the keyword MIXEDALPHBT to mix the alphabet with the Morse groups in standard order, you get this. Even with these improvements, FR Actionated Morse is rated only 2. Section 4.5. Random Number Generators. A random number generator can be anything that produces a sequence of numbers in some given range. The numbers might be single bits, 8-bit bytes, decimal digits, or numbers in any other desired range. For example, numbers in the range 0 to 25, corresponding to the 26 letters of the alphabet, are useful for some cryptographic purposes. This section introduces the topic. The complete discussion is in Chapter 13. It is important to recognize that there is no such thing as a random number. You cannot say that 51 is a random number while 52 is not, or vice versa. You can, however, say that the sequence 51, 52, 53, 54 is not random. That sequence is completely predictable. Randomness is a property of the sequence or of the generator, not of the individual numbers in the sequence. It is more accurate to say a random sequence of numbers than a sequence of random numbers. The generator might be a physical process such as cosmic rays, the pinging of a Geiger counter, precise timing of computer keystrokes, a flag fluttering in a stiff breeze, spray from crushing waves, or people rushing to catch trains. Most physical sources are not fast enough for cryptographic purposes, but the sequence of numbers might be stored in a computer file for later use. The generator could also be a mathematical function or computer program that produces a number each time it is called. Random numbers produced by mathematical algorithms are called pseudo-random numbers to distinguish them from true random numbers. They are considered weaker than true random numbers because an opponent who determines a portion of the random sequence may be able to calculate the preceding and following numbers and thus read the message. True random numbers can never be produced by a mathematical function. In section 13.8, I show methods for generating cryptographically secure pseudo-random number sequences designed to prevent an opponent from extending a segment of the sequence. One key difference between pseudo-random sequences and true random sequences is that pseudo-random sequences eventually repeat, while true random sequences never repeat. The number of terms before the sequence repeats is called its period. The sequence 31924, 31924, 31924, 3, for example, has a period of 5, shown underlined. In general, the longer the period, the stronger the cipher. Simply because a sequence of numbers is random does not mean that the numbers are equally probable. For example, suppose you are observing the colours of cars crossing a busy bridge. The colours are random, but certain colours are much more common than others. White, black, silver and red are far more common than orange, fuchsia or chartreuse. Similarly, in the game of craps, if the dice are fair, then each throw is random, yet throwing a 7 is 6 times as likely as throwing a 12. In sections 13.14.1 and 13.14.2, I discuss how to harvest the randomness in such sequences to obtain sequences where the numbers have essentially equal probabilities. I will henceforth assume that any random number generator produces numbers with equal probabilities. This is called a uniform distribution or an equiprobable distribution. With a good random number generator, pairs and triples, and so on, of generated numbers will also have uniform probabilities, perhaps going as far as octuples or beyond.